Hi, today we are looking at section 2.1, which is dealing with absolute value functions. So whenever we have vertical lines on either side of something, we take the absolute value of what's inside it. When we take the absolute value of something, it just gives us a positive value. So when we have, say, absolute value of -3, it gives us +3. If we had something that was already positive, so for example, absolute value of 6, that's just going to give us +6. So we'll look at how to utilize this while graphing. So to graph an absolute value function such as y equals absolute value of x plus 2, I find it's easiest if we create a table of values like normal, but add a third column to it. So for example, if I was graphing y equals absolute value of x plus 2, I would have my x, I would have y is equal to x plus 2, and then in this last column, I would have y is equal to absolute value of x plus 2. So I would choose several values of x to plug in for my x here to get y's, and then go through and take all these y values and take the absolute value of them in this column, and then just graph our x coordinate here with our y coordinate from here. So once we do that, we graph these x values with our y values from this column. Okay, so we'll do an example. So y is equal to absolute value of x plus 2. So I'll create that 3-column table of values. I've got x. I have y is equal to absolute value of x plus 2. Or sorry, equal to x plus 2. And then the last one, I will do the absolute value of x plus 2. So I'm going to choose some x values to plug in. So -5 plus 2 is -3. -4 plus 2 is -2. -3 plus 2 is -1. -2 plus 2 is 0. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. So we'll now, in this last column, take the absolute values of these. So -3 becomes +3. -2 becomes +2. -1 becomes 1. And we've got 0, 1, 2, 3, and 4. So at -5, we are at 3. At -4, we're at 2. -3, we're at 1. -2, we're at 0. -1, we're at 1. 0, we're at 2. 1, we're at 3. 2, we're at 4. So if we draw this out, that makes our absolute value graph look something like this. So this would be our graph of y is equal to absolute value of x plus 2. Okay, so we'll do another example. So graph the absolute value of 2x plus 3. So once again, I'll set up a 3-column table of values. So I've got x, y is equal to 2x plus 3, and y is equal to absolute value of 2x plus 3. Okay, so plugging these in, 2 times -5 would be -10, plus 3 gives us -7. 2 times -4 is -8, plus 3 is -5. -3 times 2 is -6, plus 3 is -3. 2 times -2 is -4, plus 3 is -1. 2 times -1 is -2, plus 3 is 1. 2 times 0 is 0, plus 3 is 3. 2 times 1 is 2, plus 3 is 5. So now take the absolute values of these. So -7 changes to +7, -5 turns into +5, -3 turns into +3, -1 turns into 1, 1 stays as 1, then 3 stays as 3, 5 stays as 5. So graphing these at -5, we're at 7. -4, we're at 5. -3, we're at 3. -2, we're at 1. -1, we're at 1. And then at 1, or sorry, 0, we're at 3. 1, we're at 5. Now you'll note in this case, none of our coordinates were on our x-axis. That doesn't mean it doesn't reach our x-axis. For an absolute value function of a linear equation, it should always reach our x-axis. So when we connect our points, we need to make sure that we continue on to that x-axis. And if we've drawn things correctly on both sides, they should meet up on our x-axis. Now, if you want to know the exact value where they cross there, then we just look at what value of x makes this side of our equation equal to 0, which should end up being -1.5. Now, you'll notice a pattern between this graph and this one. You'll notice that they both have the same shape. So when we graph the absolute value of a linear function, it is going to give us that V shape. Now we're going to go on to quadratics. Essentially, graphing them, we do the same way as we do with linear functions. So I'd still do the 3 columns. However, with quadratics, I tend to graph both the original and the absolute value function. So, for example, we have this quadratic. Graph y equals absolute value of x squared minus 3. So I'll set up my 3-column table of values. So I've got x, I've got y is equal to x squared minus 3. And then in this column, I'll do y is equal to absolute value of x squared minus 3. Okay, so let's go from, say, -3 to +3. So -3 squared is 9. 9 minus 3 is 6. -2 squared is 4. Minus 3 is 1. -1 squared is 1. Minus 3 is -2. 0 squared is 0. Minus 3 is -3. 1 squared is 1. Minus 3 is -2. 2 squared is 4. Minus 3 is 1. 3 squared is 9. Minus 3 is 6. So we'll plot these. So at -3, we're at +6. -2, we're at 1. -1, we're at -2. 0, we're at -3. 1, we're at -2. 2, we are at 1. 3, we are at 6. Now, for the reason why I tend to graph this original function is so that we know roughly where our new one is going to touch our x-axis. Because with our quadratic, unlike our linear functions, we don't have straight lines. So therefore, estimating where it crosses here can be very tricky, especially if we just plot our our absolute value function coordinates. Because if we go plot those, we'll just write out our values first. So this would be 6, 1, 2, 3, 2, 1, 6. So at -3, we're at 6, so same location there. -2, we are at 1. -1, we're at 2. 0, we're at 3. 1, we're at 2. 2, we're at 1, and then we're at 6. So I find without graphing this original one, people have troubles determining whether it's going to come down here, hit our axis here, and then go up through here, and then down to here and up, or if it just comes down, touches our axis here, and then goes up through these points. By drawing the original function, we can see that mirrors it or covers it completely right down to our x-axis, and then this part where our y values are negative is reflected above our x-axis. And our graph of absolute value should look like that. Now, we can see that with absolute value of a linear function, we got a V shape. With absolute value of a quadratic, we can get a W shape. However, there's several different options of what we can get when we're doing the absolute value of a quadratic. So I'll just quickly go through those on the next page. Okay, so essentially there's 6 main scenarios that we can have. So just draw out a starting graph for each of those scenarios. So first one is object or a parabola that opens up. So that's our y equals f of x. And with that vertex above our x-axis, we also have situation where it opens up and our vertex is on the x-axis. We have a situation where it opens up and the vertex is below the x-axis. And then the other three similar, but opening downwards. So if we open downwards and don't cross the x-axis, or if we open downwards and have a vertex on the x-axis. And lastly, if we're opening downwards and cross the x-axis. So these blue ones are original graph. If we take our absolute values of them, this one, every y value is already positive. So our graph of y equals f of x will equal graph of the absolute value of f of x. Nothing changes because every y value was already positive. Same as this one. It's going to overlap perfectly. So our graph of y equals f of x will be the same as our graph of the absolute value of f of x. Now this one will look like the one we just did. So this section will will match perfectly, but this section that's below our x-axis will be reflected positively. And then this section will be the same. Now for these ones that are below the x-axis, we can see that every y value here is negative, so the whole thing is going to be reflected above it. So this would be y is equal to the absolute value of f of x. Same as this one, all the y values are negative other than the vertex, so they'll touch at the vertex. Other than that, every y value will be reflected. This one, our y values in this middle section are positive, so they'll stay the same, and then we'll have something like this. So what you'll notice is if you have two places where it crosses our x-axis, two x-intercepts, we get the W shape. Otherwise, it's still going to look like a parabola, and it'll have to be a parabola opening upwards.